Okay, so let's start with our review. The first definition that we will start with is that of a vector. Okay? We say a vector in Rn is an ordered collection of n numbers. Now, this is just one of the many ways we could define a vector. If you took a physics class, how do they define a vector? It's not this. Yes? Yeah, we draw it with like a line with an arrow attached, but there's a very specific definition they like to give in science classes. Yeah. Yeah, it's an object that has a magnitude and a direction. It's like saying travel 8 miles northwest. That's a vector. It's saying how far to go, 8 miles, and what direction to move in. Okay, so we will get to that definition of a vector in just a second. But for now, I want you to think of a vector as being an ordered collection of n numbers. Okay, so it matters that it goes 8, then 3, then -2, then 5. The order is important. Okay, just some terminology here. What is this fancy R symbol? What does it represent? Yes. Real numbers, good? Note, in overleaf, or LaTeX, if you want to format this fancy R, you don't have to, but you can. It's \math bbr. Okay, now you know. What does the n mean? Well, it means there are n numbers. In our vector. Okay, now, in this class, the convention is going to be that we are going to use lowercase letters with an arrow on top of them to refer to a vector. We're also going to often draw vectors as lines with arrows on them, and so it's consistent with that theme. Okay, and we also will always write, or well, mostly, write vectors as columns, like this way, rather than rows. Okay, and this is likely what you've seen if you've taken in your algebra. Now, we will, sometimes to save space, write vectors as rows, but there's this t always attached to them, and what does that mean? The transpose. Good. The transpose of a vector that looks like this is it just rotated on the side like that, right? Columns become rows when you transpose, okay? And in this particular example, our V has 4 components, and another word we will use for components is elements. And so we say this vector is in R4. That's what that like backwards E, or like that rounded E looking thing means. It means in. Okay? Now, it can help to think of a vector not just as a collection of numbers, but rather as being some sort of geometric object. And that's the intuition I'm going to try and build in today's lecture. Like, the direction that our vector travels in matters a lot, perhaps more so than the amount it travels in that direction. Okay? And to do that, it helps to draw a picture. And we can interpret a vector as being an arrow to the point, v1, comma, v2, comma, so on and so forth, through vn, from the origin. Okay? So a vector is an arrow from the origin, which is 0, 0, 0, to the point described by its components. So in this case, my vector is going from the origin to the point 5, 3. So I might say my vector v is of the form 5, 3. Do we agree? Okay. Now, one of the key ideas we're going to need to know is how to find the length of a vector, or the L2 norm of a vector. Okay? What does the L2 mean? Well, remember, we talked about the idea of different vector norms a few lectures ago when we talked about like the infinity norm and the p norm more generally. Right? Like I could change all of the 2's to 3's and do a cubed root instead of a square root. And that would be the L3 norm of the vector. But almost always when we're talking about the length of a vector, it's going to be the regular length of a vector that you've learned about, which is called the 2 norm, okay, which is the sum of the squares of the components in the vector. Now, this formula resembles something you learned about in like 7th or 8th grade. What does it resemble? Yeah, it's just a multidimensional extension of the Pythagorean theorem. Good. Okay, and with that definition of the length in mind, let's try and find the length of this vector v, okay, or the magnitude of it. What is that? Well, by this definition, it's the square root of 5 squared plus 3 squared. 5 squared is 25, 3 squared is 9. Add them up, you get the square root of 34. Okay, so this helps us put into context what that magnitude and direction thing meant. This vector travels square root of 34 units in some direction. Like whatever this angle is, it's traveling square root of 34 units in that direction. So that's a good question. What is this angle? How would I find it? Noah. Close. It involves a 3 over 5, but it's the tan inverse of 3 over 5. Yes, let's take a look. This length is 5. This length is 3. That's what we have here. The right angle, or theta, we have a 5 there and a 3 there. So the tangent of theta is opposite over adjacent. Might have been a while since you heard of that, but you're going to need to remember it now. And so the theta is the tan inverse of 3 over 5. Okay, whatever specific number this ends up being is not super important, but this is going to appear repeatedly in this lecture. Find the angle where this happens, and really what that means is be able to write the angle equals sine inverse of some number, or cos inverse of some number, or tan inverse of some number. Okay? Sound okay? All right. Now, the dot product is probably the most important thing from Math 18 you will need to remember. Okay, it appears repeatedly in this class and in future machine learning classes, the dot product. Okay? Now, let's suppose we have 2 vectors both in Rn. The reason it's important to say this is that it's important that both have the same number of elements. That is the same dimension. Okay, that's key. But the way you compute the dot product of 2 vectors is by taking the sum of the element-wise products of the vectors. Okay? So if we have 2 vectors, u and v, it's the first component of u times the first component of v plus the second component of u times the second component of v, and so on and so forth. Let's make this a little more tangible. I have 2 vectors here, u and v. U, how would I describe it in coordinate form? 2 and 4. 2 to the right, 4 up. And v, how am I describing v? 5, 3, right? Okay, side note. This is the kind of thing that no one would realize unless I make it explicit, but like, it took a crazy amount of, not a crazy, but like it took a non-zero amount of time to make sure that the blue of the arrow is the same as the blue of my marker. It required screenshotting the lecture slide, sending it to my computer, using a color picker to find the exact hex code that GoodNotes uses, and then telling Matplotlib to use the same color of blue. Who asked for that? Nobody, but it had to be done properly. Okay? What's the dot product of u and v? Well, let's write it out. U dot v is, well, it's the first thing in u times the first thing in v. So maybe we'll do 2 times 5. Plus the second thing in u times the second thing in v. So that's 4 times 3. Last I checked, that's 10 plus 12, which is 22. A key to keep in mind is that this is a scalar, which is just one number. That's huge. Okay, keep that in mind. The dot product of two vectors is always a single number. Okay, it could be tempting to think, okay, I'm multiplying two things. The result will also be a similar kind of thing, but that's not how the dot product works. Okay, the dot product of two vectors is a scalar. Do we agree? Okay. Now, I can also write the dot product, and we're going to need to do this soon, as the transpose of one vector multiplied by the other. Here's what I mean. I can write it as U transpose regular multiplication V with no dot. Okay? And these are equivalent. U dot V is the same as U transpose V with no dot there. Okay? And when I do U transpose V, what I'm doing is I'm taking U and I'm turning it over to its side so that the dimensions match up for me to do regular matrix and vector multiplication. Okay, so what does U transpose look like? Well, it looks something like 2 and 4 rotated over to the side times 5 and 3. Okay, and the way you do regular multiplication of matrices and vectors is you take the rows of the first thing and multiply it by the columns of the second thing. So how does this work? I'm going to take the 5 and 3, rotate them over, and dot product it with 2 and 4. Sound familiar? Good. Okay, and you end up getting the same result. It's the same calculation, it's 22. Okay, and it's important to note that when I'm multiplying out U transpose V, I can only do it because the dimensions match up. Like the dimensions of U transpose are 1 by 2, and the dimensions of V are 2 by 1. These inner dimensions match. And that's why I can do this multiplication. Right? In order to multiply two objects in linear algebra, whether they're vectors or matrices, the number of columns in the first thing, 2 here, need to be equal to the number of rows in the second thing, also 2 here. Like if we had a third row in this vector, I couldn't do U transpose V. Do we agree? Okay. Good. Questions with the dot product? Sound kind of familiar? Good. Is this needed review? Sounds like it. Good. Question?
What does the dot product tell us about the two vectors?
Great question. What is the purpose of the dot product? We are going to see that very shortly. The answer is, yeah, not really anywhere on the slide, but it'll become clear shortly. But the one sentence answer is that it tells us a lot about how similar the two vectors are, like how closely they point in the same direction. Okay. To synthesize what we've seen so far, I want you to attempt this for a second. Well, longer than a second. Which of these is another way of expressing the length of the vector v? Okay? Discuss for a second or two with the people near you, and we can take it up. Okay. So let's write out a vector v here. Right off the bat, we can rule out options B and D. Why? Yeah.
If you do a vector, if we square v squared, you do a vector, you can't just exclude vector.
You're on the right track. V squared actually is not defined. It's not anything. I think it's tempting for us to see v squared and think that it works like NumPy, where it squares the elements of the vectors individually. But like squaring things element-wise and making a new vector out of it, that's not a regularly defined linear algebra operation. Okay? To think about what v squared gives us, we have to go back to looking at the dimensions. Okay? V, if I try to multiply it by something, I have to keep in mind that it has n rows and one column. And when I try and regular multiply that by v, well, then I run into this issue that the number of columns in the first thing doesn't equal the number of rows in the second thing. 1 is not equal to n. Right? And so the way that this is often said is that the inner dimensions must match, but 1 is not equal to n. Okay? So squaring a vector in general is not a thing you can do. Do we agree? There are some cases in which you can square matrices, and maybe we'll talk about that, but a vector, you can't square it. You can dot product it with itself, though. And so what might that look like? Because the other two options involve that. Well, it would be this times this plus this times this plus so on and so forth, all the way through plus this times this. Okay, so I'll get v1 squared sound okay? Is this the length of v? No, but it's awfully close. What do I need to do? Yeah, I need to square root it. Okay, which means the length of v is whatever option C said.